Okay, so Bohr's model worked really well, especially for hydrogen or helium that had lost an electron and ion. One electron atoms are well represented by Bohr's model of the electron orbitals, but when you get bigger elements with more and more electrons, it starts to break down a little bit. So eventually, the quantum theory, which is basically what we use today, molecular orbital theory, developed a little further. But Niels Bohr was considered kind of the father of quantum theory because he said electrons can only be in this orbit or in that one, but not between. Their energy is quantized, kind of like when we joke about kittens, right? You can have one kitten or two kittens, but not like parts of kittens happily. And that's what Niels Bohr talked about with orbitals. But in quantum theory, we have s orbitals, and s orbitals you can think of as something like spheres, and they stack. The 1s orbital is a sphere, so don't think of it as a circle like we draw it on the board, right? Think of it as a sphere, and then that 2s, the 3s, and those ever-expanding kind of spherical shapes. The p orbitals, which I like to think of kind of as dumbbells. So if you hold two balloons together with their tied ends in the middle, you have two balloons. That's like one p orbital, but there are 3 p orbitals, which hold a total of 6 electrons in, say, the 2p. So p orbitals, you would have 3 dimensions. So you'd have one orbital, which is like 2 balloons tied together at the middle. You'd have one in the x direction, say that's the plane of the board. You'd have one in the y direction, so this is one more p orbital for a total of 2. And then you'd have one that have one lobe sticking out of the board and one lobe kind of behind the board, right? So you've got a p orbital in this orientation, one in this orientation, and one 3-dimensionally in and out of the board. 3 p orbitals each hold 2 electrons for a total of 6 p electrons in each of the p orbitals. And then there are d electrons, and there's no good way to draw them. If, hopefully in class, I'll hold 6 balloons, right, 2 for each of the p orbitals, a total of 3 p orbitals that hold 6 electrons. If I hold 6 balloons, you can see there are kind of these donut-shaped spaces in the place where balloons aren't, and the d orbitals kind of fit into those spaces. So all of these exist together at the same time. They fill with electrons according to the lowest energy first, up then through the higher energy for atoms with more electrons. And then some of the electrons can absorb energy, move to higher energy levels. But the Ds are kind of like donuts, and there's just no way to really draw them. But they kind of, this is super simplified. Everything I tell you is something of a fib, because quantum theory is very complicated, and d orbitals can even have like kind of multiple shapes. So it's not something you need to understand, just that there are 5 orbitals for a total of 10 electrons in each level of the d orbitals. So this really led to the explanation of why the periodic table lines up so neatly. I'm going to zoom you in here because you can't see the periodic table very well. Right, so you can see the periodic table and this strange shape it assumes, right? And it's basically this, right? S orbitals have a specific chemistry, p orbitals and d orbitals also. Oh, and if you look at the periodic table, These also are called F orbitals. I wonder if by the time you come into class on Tuesday, if you can tell me how many electrons are in each F. So this is the 4 F orbitals, and this is the 5 F orbitals. And if you can tell me how many electrons, that would be cool. So how many F orbitals, how many electrons? So if you think S has 1 orbital in each level for 2 electrons, P has 3 orbitals in each level for 6 electrons, D has 10 orbitals in each level for, 5 orbitals in each level for 10 electrons. So if we look at the periodic table, this is what we see. Okay, the normal metals, all their valence electrons end in an s orbital. The highest energy orbital is always an s for the first 2 columns. So 2s, or 2 columns here, right? These 2 elements. Hydrogen and helium are both 1s. So this would be 1s1, this would be 1s2. Then you have 2s2 for lithium, 2s1 for lithium, 2s2 for beryllium. Then the p orbitals are the next in energy, and you can see there are 6, 1, 2, 3, 4, 5, 6 elements. 3 p orbitals would hold 6 electrons, so they're valence electrons. The highest energy electron is in a p orbital for these guys in this block here. And then the d orbitals here, you have 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So their highest energy electron is going to end in a d orbital. And so you can kind of see, of course, these guys end in f orbitals. So when you're writing the electron configurations, this is kind of what you have, right? 1s1, 1s2, 2s1, 2s2. So far easy. Now you just have to remember this. P starts with 2. So there's no 1p orbital. It doesn't exist, right? There's no p's in this top line of the periodic table. This is just empty from, and if you think of helium as really being right here instead of over here, that's kind of helpful. There's nothing in the p block there. So p's start at 2. So 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. And then down here to 3s1, 3s2, because everything in this column has a highest energy electron in an s orbital. So 3s1, 3s2. And you come over here to 3p. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. And then down here, 4s1, 4s2. Now here's where it gets a little confusing. So if you just get this part, it will be easy. The highest d orbital is a 3d. Okay, so d's start with 3. There's no 1d, there's no 2d. You just start with 3d. 3d is easy to remember, right? 3d. So you have this electron, the highest energy electron is 3d1, 3d2, 3d3, 3d4, 5, 6, 7, 8, 9, 10, right? 3d10. And then you've got, so you had 2p here, 3p here. This is 4p1, 4p2, 4p3, 4p4, 4p5, and krypton is 4p6. So that's just a basic rundown of how you use the periodic table in conjunction with electron configurations. There are elements that are exceptions. When you start getting down here, you start to have some exceptions where it looks like, say this is 1s, 2s, 3s, 4s, 5s, 6s, right? So 6s1, 6s2, and then it looks like you should have 3d1, 4d1, 5d1. Sometimes you find that there, instead of this being a higher energy, the 6s2 is higher. And so there are exceptions, and they're specific, and you do not need to know them. I just want to tell you that there are exceptions, so you're not surprised in college. You may label your periodic table with these things. The S block, see how I made like a little S? So you remember there's S's, the D block, these transition metal block, the P block, the 6 here, which include metals and nonmetals, and the halogens there. and the noble gases there. And then these are Fs, but you don't need to know about Fs in this course, I think, at all, basically. And remember that you would go from cesium to barium to lanthanum and then down to the F block here. And that would basically, if I cut the periodic table here, stretched it out, I could just place these in there. We just want it to fit on a sheet of paper. But you can see the atomic number and how that periodic table should fit together. You can also write on your periodic table that there are 2 electrons in s orbitals, 6 in p's, 10 in d's, and that p orbitals, there's no 1p. You start with 2. D orbitals, there's no 1d, no 2d. You start with 3d. So those are things you may write on your periodic table, nothing else. If you write that one on the one that's signed OK for a test, you can use that one that you write on the test. And I'll start a new video in a second.